Thank you for being here. For the people who are on Zoom, I realize it's a little unfortunate that you couldn't get the Timbits that we ordered, but I did want to point out that there was a study of the effect of virtual Timbits, which you can look up, and it turns out that if you just give people the smell of donuts and the feel of donuts, then they actually eat less donuts. This is the claim. So the people who were only doing the virtual Timbits are probably healthier than the rest of us, even if they couldn't be here. But with that, I want to turn to the actual topic of today. There was a Physics Nobel Prize recently. It was kind of two half prizes with an overarching theme. I didn't even try to get these people here in person because there's a pandemic and so on. So I thought instead we could get local experts, and with a little bit of gentle arm twisting, or quite heavy arm twisting, James Charbonneau agreed to talk about the climate science part, and Philip Stamp agreed to talk about the spin glass condensed matter part. So we're going to get two half talks, so we start off with James.
All right, hello everybody. Okay, yeah, I'm on. So I'm gonna be talking about the Nobel Prize that was awarded in climate. Both these Nobel Prizes, they share this idea that these systems deal with complexity, and I think I'll talk a bit about what complexity means in earth science, and Philip will talk about it in these spin glass systems. But specifically, I'm going to talk about Manabe and Hasselmann and their work sort of in modeling the climate and trying to understand some of the variability and the strange things that happen with these models. Okay, clear, very clear. Okay, so I think I've doubled up the slide. Oh, look at that. We had the exact same idea, so I'm just gonna skip over. So I guess one thing I'd like to talk about is the difference between climate and weather, and climate prediction and weather prediction to begin with. One of the things that's sort of interesting, so my wife is a meteorologist. She actually does weather prediction as a living. And I asked them, like, in your office, are they talking about the climate prize? And they're like, no, where's the Nobel Prize for weather prediction? So the weather is different than the climate, but they're both the same thing, right? The weather is a highly variable thing that's moving up and down, or that's changing quite a bit. Here we have this is the heat dome event from previous summer, and has been talked about a couple of times at Colloquium. And the weather, you see, as it moves along, it's highly variable. It goes. This is the temperature. It goes up and down as the season goes around. And then there was this event where it was the hottest temperature in Canada ever recorded, 49.6 degrees Celsius. And weather prediction is really good. So weather prediction actually predicted this a week ahead. So they knew this was going to happen. If we look at the general trend of these oscillations, though, we see that the average, there's like an average, there's a hump that goes up and down, and this is called the climate. And so weather prediction and climate prediction really have two different things. Weather prediction is trying to predict things on the scale of days and maybe weeks. And they're trying to get specific values. Like on this day, it is going to be 49.6 degrees Celsius, right? Where climate prediction is really the average of these, and the average of these fluctuations. And what it's trying to do is figure out, well, what are the peak temperatures and the lowest temperatures? What are the thresholds of all our variables that we expect? And one of the things we notice is that just from this data, you can sort of see that in the winter months, the spread is wider than in the summer months, or in the fall, I guess. Because of this, I want to start with just weather prediction. So Richardson in 1922 was the person who did the first sort of weather prediction. And at the time, it was pretty much the equations of motion were all figured out, the thermodynamics was figured out, they had some understanding of fluid dynamics, geophysical fluid dynamics. And what Richardson set out to do was, can I actually do a weather forecast? Like, knowing all of the physics of the weather, can I set it out? And what he did, and as a fundamental tenet of this, is they sort of understood that weather prediction and thus climate prediction was inherently numerical. There was no other way to solve these equations or to get these results. So this is a plot from Richardson's original book from 1922, where he essentially divides everything into a big grid. And it's a grid that alternates. In one grid, he's trying to calculate the pressure. In the other grid, he's trying to calculate momentum transfer. And he's alternating to try to get a feeling of what this field looks like over all space. He decided to do a 6-hour forecast. So could he use the equations of motion to actually do a calculation in the future? He did it, a 6-hour forecast. It took him about 6 weeks to calculate. And he was one time step too, just one 6-hour time step. And he got a change in surface pressure of 140 millibars in 6 hours. The current pressure is around 100 millibars. So a change, like atmospheric pressure is 100 millibars. So a change in 140 is quite dramatic and off by about 2 orders of magnitude. But the techniques used are still used. Like this book by Richardson really laid out, this is numerical weather forecasting. And it set the paradigm until well into the 60s. So in terms of weather prediction, by the 60s, people had really solid control of the numerics, how to understand the numerics, and how to understand the weather. But one of the sort of goals is can we do better than just predicting short scale things? Can we predict things at longer scale? And the sort of dream was that can we build a model that isn't just a small grid like Richardson's, but that encompasses the whole planet Earth. And it's a grid that has everything on the surface, but also a grid that captures the atmosphere and captures the depth of the oceans. And in 1955, Phillips did the first sort of model. He modeled the Earth's atmosphere as a 2-level grid, 16 by 17 points. And he took the Earth as a cylinder that had the sun shining on one side. It was getting radiation from one side. And he started from just air being steady, a constant thing. And can actual weather-like things develop? And they found out that with this model, a jet stream developed, a stable jet stream developed around this cylinder. I find it sort of funny that there's this joke that physicists always approximate everything as a sphere, but then when given a sphere, they approximate it as a cylinder. Anyway, but they had this actual weather pattern. And so this was a real success, and this made people think like, oh, we can actually do this. This is something we can do. So when we get to Manabe's work, one quarter of the Nobel Prize, what he was really thinking about, well, a lot of these models only worked on 2 levels. But the temperature profile of the atmosphere is actually really, really complicated, right? There's all these different aspects of the atmosphere where things cool down as you get higher, but then they heat back up and they cool back down. And it really has to do with, the composition of the atmosphere and the composition of the gases in the atmosphere, the composition of the radiative absorption of different chemicals in the atmosphere, like ozone, CO2. So he was really trying to think about that. So his first models were really just a single column. They're called single column models. And they assume that everything is just, there's no horizontal movement of anything. We're just thinking about the vertical stuff. And he put in, I think it was like a 9-level model. So there's 9 sort of points. But one of the big things he had to do is when you're doing these equations, when you're doing these numerical calculations, there's weather phenomenon, there's phenomena in the atmosphere that exists on a smaller scale than those grid points. And so what they had to do was come up with some parameterizations of the physics where you do a calculation to the next grid point, and if it's unphysical, you sort of have to change some stuff and go back and rerun the model until you get a physical temperature profile. One of the constraints is like the temperature should be a continuous field, right? And not have weird discontinuities in it. So I think this was one of the real things that Manabe introduced was this idea of how to parameterize subgrid scale physics and how to do it in a way that actually captures the physics and how to do it in an iterative way that makes physically sound predictions. And so what I plotted here was from one of his first papers in the early 60s, where there's the measured temperature as a function of latitude in October on one side, and then his model simulation on the other side. And so he ran his model for a bunch of latitudes and then was trying to get this profile to match up. And you see there's some features, like there's the temperature decreases and then there's this inversion and stuff starts getting warm again. So this was one of the real first steps. And this is the paradigm for how not only weather prediction, but climate prediction went forward. They're very similar things. The next thing he did is like, well, let's take this and now let's put it into the general circulation model. Let's put it in this model that's a full round Earth with all the levels and all the grid points. And so there was a few papers where he was trying to nail down not only parameterizations to do this properly, but in the end, he just started playing with, if I change this concentration of a certain molecule in the atmosphere, how does the temperature profile change? And how does everything change? And one of the things he did was, what happens if I double CO2 or half CO2? And so this is sort of the famous sort of first full-scale simulation of what's called the climate sensitivity. This idea that when we double CO2, this is the famous number that you see everywhere. When you double CO2, you actually double or you increase the temperature by around 2.3 degrees Celsius. So this was sort of the big result and showed that that CO2 is indeed a big thing in warming the surface temperature there. And I should just point out, like, he's doing the whole thing, but the 2.5 is in that sort of blurry mess at the bottom there, which is why it's nice to have a table. Around the same time in the 60s, there was somebody called Ed Lorenz who was working on weather simulations and was trying to figure out the simplest weather model possible, right? And so this model, he just reduced it to like, what is an atmosphere? And it's really temperature gradients and the movement of winds. And so that's what these equations really simply describe. And he found some very, very weird stuff. He would run a simulation, he'd get some answers, and he had a printout, and he'd just take the numbers from the printout and put them back in to try to rerun. And the thing is his printout was calculating things to a different precision than the actual computer. And so when he was putting them in, he was getting results that deviated quite greatly, right? So only changes in the 5th decimal place were making his runs go completely off right away. And this was sort of the birth of chaos and this idea of systems can be highly sensitive to initial conditions. And he says here, this 2 states differing from imperceptible amounts may eventually evolve into 2 considerably different states. In view of the inevitable inaccuracy and incompleteness of weather observations, very precise forecasts are likely non-existent. This has nothing to do with understanding the physics. This has to do with understanding the initial conditions. So it leads us, talking initial conditions. So I was trying to predict when I get to this slide in the top, 413. I predicted how long it would take me exactly, but the initial condition I didn't predict when the talk would start, right? But the real question that we can sort of see here, so this is just the x-axis of these equations, is on small time scales, slightly varying initial conditions actually are close to each other. There's a point where they completely diverge from each other and they become useless in terms of predicting exactly, like, what is the temperature going to be 3 months from now at this specific time, right? Weather models just can't do that. And so there's this idea that climate has to be climate prediction and doing climate models has to be inherently probabilistic. And there was a feeling that, well, if we make a bunch of these runs, right, where we run a bunch of climate models and we get to this point where we can get an average, but the actual values don't matter, then maybe we can treat the average values as noise, or not the average values, but the oscillations around an average value as noise. And this is really what Hasselmann did. So Hasselmann had this idea, let's take the climate and break it into fast moving, or the atmosphere, break it into variables that move quickly, like the temperature, the air temperature, and variables that move slowly, like the temperature of the sea, or the ocean. And there's this idea that we can calculate the change in some climate variable by thinking of this function that is, so x, this bracket with x and y is the average of x conditional on some values of y, right? Plus x star is these fluctuations around that average. And then there's some, there's the slow moving variable that is y. And you can see there's just this linearization that you do where you say, well, we're going to break it into slow moving things plus these fast moving things. And the fast moving things, we can essentially model them as white noise. Okay. And the interesting thing about this is when you get this out and you model it as white noise, this is a stochastic differential equation. So you can use the tools of stochastic calculus to help you out. And the solution of this equation has a power spectrum associated with it. So you can get a power spectrum and a frequency distribution from this. So what Hasselmann did was apply this to the sea surface temperature anomaly and find that with his model, so his model is the straight line and the actual data are the wiggly line, that it has this red noise frequency distribution. So the climate is really, the Brownian motion of something getting bumped around by little tiny white noise oscillations, essentially. And so this brought into the idea that you can do this sort of stochastic approach to predicting the climate and to understanding climate variables. And so maybe the last thing is, with this statistical understanding, you can do a bunch of runs of these climate models, and you can just run them and run them and run them and see if your climate models predict the actual change in temperature of the atmosphere. And then what you can do is you can remove certain things from your climate models and try to run them a bunch of times and try to tease out, well, this thing causes this temperature change and this thing causes this temperature change. And so this was the big sort of final thing, or one of the things he was awarded for was this idea that the temperature change we see in the atmosphere is, though we've been at this temperature before, the temperature is human caused. The things that make the temperature increased are human caused. So that's my summary of the Nobel Prize talk.
Okay, so Douglas asked me a couple of days, well, we established communication a couple of days ago. The ridiculous thing is that I gave a colloquium here about a month and a half ago on a totally different topic, which is the one I'm actually working on these days, which is quantum gravity. But as a matter of fact, this is a field which I have in and out worked on for some time. And I'll explain to you that quite a few people in the field, particularly in North America, were rather surprised at this prize. This is not to say that it wasn't richly deserved, but I'll explain that in a minute. The picture here that you can see is one that came from one of Parisi's papers, and it's extremely interesting. It's a so-called ultrametric diagram, and I'll explain that as well. Now, there is actually a long and very, very interesting history in this field. I was reminded by the remarks of James on the work of Ed Lawrence, who actually was by no means the first to talk about chaos. In fact, probably the first to discuss it mathematically, although he didn't use the word, was Laplace more than 200 years ago in discussing the dynamics of the solar system. And the first person to really recognize what was actually happening was Poincare at the beginning of the 20th century. And of course, it was all nailed down mathematically by Kolmogorov, Arnold, and Moser. In Kolmogorov was 1947. So from this, you can see that my timeline here, which begins in the late 50s, is perhaps a little late in coming. But the point is that that the analysis of, if you like, of complex systems that was done using the spin glass as a model turned out to be extraordinarily fruitful. and has led to a lot of insights in many other fields. So my guess is that it was for that reason mainly that this prize was given. It was the if you like, the spin-off from the almost purely mathematical work of people like Parisi. So we're going to, focus down now on what's called a spin glass. Before at the end, I start talking a little more about the massive implications of this work in lots of other fields. Okay. The overarching influence in this entire field was Phil Anderson, who, before anybody else, realized the enormously broad impact of this work and really set the philosophical outlines, if you like, of it for a very long time. He also provided all of the initial models. But of course, he's no longer alive. Otherwise, he would have gotten the second Nobel Prize, I suspect. So in 1958, he first showed that in any random quantum system, you would get localization. This led to an enormous change in our understanding of quantum mechanics. This is true even if you have a single particle moving through a random potential. It will actually not spread out in the way that you're supposed to believe for a quantum mechanical system. But he was more interested in spin systems. He was heavily influenced by an experimentalist, Grant Matthias, at the same time, and I'm not going to go into that story. In 1975, Edwards and Anderson proposed a model for a random spin system called the Edwards-Anderson model, which is the basis of all the subsequent work. And I'll tell you a little bit about what that is. I've decided to avoid all mathematics in this talk. There'll be a little bit for those who are interested. But Anderson and Edwards proposed this model, and various other models were proposed quickly afterwards. And it was a very, very simple model, which I'll show you in a minute, yet it had fantastically complicated mathematical behavior, which was really resolved by Parisi, who is the winner of this Nobel Prize. As I'll discuss, there's been a lot of debate, sometimes rather heated, about whether Parisi's results apply to the real world. And in fact, there's a very strong cultural divide here. People in North America tend to feel that it does not. There's a much more empirical bias, if you like, in North American physics. Whereas in Europe, they've often said, well, we really don't care. We're interested in these models for their own sake. So models like the droplet model, for example, by Daniel Fisher and David Hughes, they are, if you like, models that are more intended, they're phenomenological models that are more intended to describe the real world. Okay, so this is the history. And by the way, the history changes very much in our century because we start to discuss the quantum versions of all these models, and I'll get to that. So I'm going to start with a really simple question. And this is the question that was being asked 150 years ago. How do I describe a system with many particles or many spins? And in courses, I think probably even in high school, I'm not sure, you're told about how many different ways you can count the states of n coins. So supposing I give you, which is what I'm doing in this picture here, 16 coins. Each one can be heads or tails. So the question is, well, there are two questions. First of all, how many states are there? How many different ways can I have arranged these different coins? How do I count the different numbers of states? And second, what's the probability that I'll get one specific distribution? So what I'm showing here is something that I suspect all of you have seen in one way or another. I'm showing the number of different states which have a given number of heads in this graph. So actually there's only one state which has 0 heads. That's all tails, okay? But if I go to the different states that have 8 heads and 8 tails, there's actually a great many of them. I could, have a head first, a tail second, a head third, and so on. But I could have a run of 4 heads and then tails, and there's a very large number of them. And in fact, you learn, and probably in the first year of university in the probability course, how to figure out how many different possible ways there are of arranging say 6 heads and 10 tails. And the number is given by the factorial of the total number, that's 16 factorial in this case, divided by the number of heads factorial, the number of tails factorial. For those of you who are not interested in the mathematics or who are actually not scientists, because I know there are people coming in on Zoom who may not be scientists, never mind. This is what the graph looks like. This is what you want to know. It's telling you that it's overwhelmingly likely they'll get roughly the same number of heads as tails. And if I increase the number of coins, that becomes much more pronounced. So this is for 16 coins, and this is showing the probability of getting different numbers of heads. This is for 60 coins, and this is showing you the probability of getting, you see the peaks at 30 heads, but you see that if you go very far away from the peak, the probability goes very, very fast to 0. And so you can now ask, well, supposing I have 1,000,000 coins, then it'll be incredibly peak. You'll find that the probability that it's not in the band of a few thousand on either side of 500,000, the probability you get anything farther than that is, just negligible. And so this is how the idea of relating a microscopic state in physics to a macroscopic state came about. We say, well, as far as we're concerned, what we're really interested in is just the total number of heads. Or maybe we could say instead, we'll be interested in the total number, the difference, if you like. And we see that the difference is very, very overwhelmingly going to be close to 0, at least the percentage. So I can ask, well, what percentage of the coins will be heads if I throw 1,000,000 coins? The answer would be very close to 50%, almost always. And the deviation from that, what we call variance, very small. So now imagine that these coins are actually spins. They can be up or down. Up corresponds to heads, down corresponds to tails. Well, in that case, the difference, up minus down, is just the total magnetization of the system. So we're saying that here, the probability that the magnetization is very far from 0 is negligible. And we say that the magnetization is a macroscopic variable. It's something that we can see or measure. We can measure the magnetization. The magnetization of the system generates a field. Of course, you now can ask yourself, why is it that systems are magnetic? And I'm not answering that here. But I'm telling you that one can relate an enormous number of different microscopic states with all of the different spins rearranged and so forth to one macroscopic state, which has got 0 magnetization. And so came the idea, a long time ago now, which you will learn, or already have learned, that for every macroscopic state, thermodynamic state, there's an enormous number of microscopic states. And we also learn that there are different phases for any real macroscopic system. Solid, liquid, and gas, for example. So I'm showing here helium-3, which is a gas at high temperature. But if you go to low temperatures, this is in degrees Kelvin above absolute 0, it's vapor at low pressure, liquid at higher pressure, and solid at high enough pressure. So we've got 3 different phases in which the microscopic states actually don't look all that different, but the macroscopic states do. And if we go even lower in temperature, we get to lots of other phases, which I want to talk about. Now, this all seems like a simple story, and it's what, unfortunately, is in almost every book on statistical mechanics that you'll see. To the point where when I had to give the statistical mechanics course, I threw all the books away and wrote some notes because it's all wrong. Here's the real world. None of the systems on this picture, except one, are described by the language that I just told you about. Can anyone tell me which system is described by the simple arguments that I gave you? The liter of air. Correct. So somebody here said the liter of air. And that's correct, because it is just a gas with particles bouncing around, and we can answer the question how to count the states. But none of the others. All of the others have problems. I'm going to pick one here at random. Well, not quite at random. I'm going to pick a piece of glass. Now you might say, a glass? Oh, that seems pretty simple. Looks just like a frozen liquid, so what's the problem? Well, if I look in a real glass, first of all, I see that it does indeed look like a frozen liquid. But if I actually ask what are the different excitations in it and how long it takes them to change, to relax, it actually looks a bit like interstellar space. You have various bright spots. These are regions that are excited, and lots of dark spots. And it's pretty static over very long periods of time. Actually, a glass is a system which takes an enormous amount of time to relax. It's nowhere near an equilibrium state. So if you leave a piece of window glass at high temperature, after maybe 8 centuries, you'll see that it's starting to very slowly change its shape. And it will continue to do so for hundreds of thousands, if not millions of years, before it gets anywhere near its completely relaxed state. Now, one can do this with a set of spins as well. Here are some experiments where you see the same thing. If you try and look at this cut here is telling you there's supposed to be a phase transition in this disordered solid. But if I change the frequency, if I look at the phase diagram now by rocking the field back and forth, I find that the temperature of the transition changes. And in fact, it relaxes. So the actual phase transition changes with time. And these are showing over log time the relaxation. And again, very, very slow. Actually, we know that in many of these systems, the relaxation times go as the exponential of some function of the number of particles. So exponential of 10 to the 23 is, for all intents and purposes, infinite. So here's the model that Parisi was looking at. It's called the Edwards-Anderson model. And we've got a set of spins, which are, in this case, at random positions on a lattice, and they have interactions between them. Now, this is a bit of mathematics. It looks horrible, but it's actually really simple. The sigmas are just telling you whether or not a spin is up or down. It's plus or minus 1, depending on whether the spin is up or down. So it's just like the coins, okay? Sigmas are just telling us whether the coin is up or down. And we're saying now that there's an interaction between these coins, between these spins. And what Edwards and Anderson said, well, let's supposing this interaction is random. What happens then? Well, a key thing that was discovered was present to what's called frustration. And Parisi was very clever at explaining frustration in language that had nothing to do with physics. So he would say, supposing we have 3 people. John likes Jim, but John does not like Joan, and Joan does like Jim. What do you do? So in this little triangle diagram here, we're showing this. Like here means that they're oppositely oriented, okay? So John likes Jim just means that they're oppositely oriented. Opposites attract. That's the basic idea, okay? But what about this third one? It's either going to be attracted to this one or that one. It can't manage both. This is what's called frustration, okay? Now, you might think this is a kind of ridiculous and trivial observation, but what was realized by Anderson and also by Parisi was that this is actually the key to understanding the dynamics of these disordered spin systems. And I mean, mere fact that I've alluded to, like and dislike relations tells you that it didn't take long before all of the work that these people did was applied to sociology and in many other fields. But let's go on. It turned out that even to solve this very simple model was incredibly hard. So people like Edwards and Anderson and Thales Anderson and Palmer and Sherrington and Kirkpatrick and so forth, they made all sorts of approximations to try and solve it, but they never were able to deal with the real model. And then Parisi came along and he applied some remarkable techniques to show how to do it. He considered what are called the set of replicas. Well, he considered a large number of systems which had all been prepared with the same, they're all randomized spins with the same net magnetization, if you like, but they were all different arrangements. And we saw at the beginning that it's possible, for example, we can have the same number of heads with a large number of coins, but different arrangements each time. So these are the replicas. And what Parisi was able to show mathematically was that there was extraordinary hidden relationship, or a hidden order, if you like, in all of this. That even though you didn't apparently change anything from the macroscopic scale at all, you were changing relationships inside, which could only be accomplished by very complicated flipping maneuvers of the spins. They were complicated because they had to get past this wretched frustration problem. So you see that we can't deal with this frustration here, but supposing we had some other states on this lattice, you can imagine that maybe by flipping a whole bunch of spins, we could arrange things so that everybody was satisfied, or better, or happier, if you like. So you can put a whole bunch of people in a room. If you've got 3 people, it's impossible to keep everybody happy. But imagine you now add a whole lot of other people, and now you rearrange everybody until you optimize the situation. The net happiness is maximized or optimized. So this is the same idea. And it turned out he was able to show that there's a kind of a hierarchical structure to this, which almost looks like a sort of a genetic tree, you know, the tree of a phylogenetic tree, in which you have you know, species, genera, and so forth. And in fact, people have used this in the taxonomic classification. And the reason for this complex structure was the frustration. Actually, Phil Anderson was one of the best, there was one of the top 5 people, I think, in the world at Go. And so he drew attention to the parallels with Go. Another way that was discovered to think about this was in terms of a landscape, a so-called energy landscape. Happiness is now energy. So the happiest possible state of all these people is the one with the lowest energy in the Hamiltonian that I showed you. Optimizing the happiness in the social network means lowering the energy to the lowest possible value. But in order to do that, you may have to follow a really complicated path, because this landscape is not in 2 dimensions, it's in 2n dimensions, where n is the number of spins. So very complicated, but what Parisi showed was that, that the structure, if you like, of this landscape had this taxonomic or ultrametric structure. They being mathematicians, they realized that this was a specific kind of geometry called ultrametric geometry. And so this was a very nice picture. As I said before, some people felt that this was all very nice, but it didn't help us understand the experiment, and that has indeed been a problem. But that's basically what was done. Since then, lots of people, including Parisi, have tried to apply this to lots of other kinds of network, financial networks, social networks, brain modeling and neural networks, networks in prebiotic evolution, protein folding. Steve Plotkin in this department was at one time working on this, and disease networks, and there are others. And there's an enormous literature now that's developed from this, which has employed to a greater or lesser extent the techniques that were developed in this work on spin glasses. So this is an example of cross-fertilization. Should note that these networks may not be independent. So for example, we're all very familiar with disease networks these days with COVID. And there it's clear that social networks, particularly governmental networks, financial networks, economic, and viral networks all play a role, and they interact with each other. So, you know, we've seen, for example, that governments have played a big role in the evolution of COVID by their different policies, and we've seen dramatic differences in the results in different countries. I was having a conversation with one epidemiologist where, you know, we decided that basically the whole COVID thing had sorted out the women from the boys, because the countries that have done well were almost invariably run by women. New Zealand, Taiwan, South Korea, Germany. And the ones that have done really badly were run by boys. Boris Johnson, Donald Trump, Bolsonaro, etc. But this is an example of a social network. On the other hand, the disease networks are quite a different story. This is where you're trying to understand the way in which viruses spread. And again, the epidemiologists didn't actually have the right models. So there was a lot of discussion early on about the way in which the virus was spreading. And in fact, of course, it was mostly airborne. And this was not being built into the models at all, except in some countries. Now, all of this is very nice, but there's one thing that was left out of all of this. And so I'm going to finish by telling you where we are now, because we've crossed the boundary between the classical domain and the quantum domain since all of this happened. I showed you the timeline at the beginning. And after 2000, everyone decided that they wanted to know about quantum networks. So I'm going to finish off by talking about that. The point is the following. I told you about this landscape. And if we want to go from here to here, we may have to climb over all these barriers in between. And that's why these glasses relax so slowly, because they have to thermally fluctuate over many, many barriers in order to get from A to B. But in the quantum regime, they can tunnel. Tunneling is actually slowed down often by temperature fluctuations, by the dissipation. And then the nature of the networks completely changed. The quantum networks were quite different. And the one, of course, that's in the news these days is the quantum computational network, in which you have qubits, which can be up or down, but of course they're quantum, so they can be in superpositions of up and down as well. And that changes everything. So now, instead of being, this shows you the different possible states for 3 qubits. There are 8 of them. It's like 3 coins. There are 8 different states for 3 coins. Heads, 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 tails, heads, etc. But you see, in a quantum network, we don't have to be on one site or another. We can be on a superposition of the sites. And so these networks now don't involve you hopping around between different points. They involve you spreading out in a quantum mechanical way. And that makes all the difference. In 1999, the group of Apley, Rosenbaum and company first showed what was called quantum annealing, which is basically the relaxation that I was talking about in this last slide, through this kind of landscape, but now driven by tunneling. And they showed, and I haven't got time to go through these graphs here, but they showed that they could go around the cycle in the phase diagram and get completely different relaxation properties in the quantum regime, which shouldn't be surprising at all, because it's happening in a totally different way. 8 years later, in Vancouver, this quantum annealing led to the first quantum computer in the world, the so-called adiabatic quantum computer made by D-Wave Systems, which is now a fairly large company based in Burnaby, but which actually began in my research back in '99. And this is what is called a universal quantum computer. And there's been a lot of talk about whether or not this sort of thing will revolutionize the world, just like Pinky and the Brain. It's not clear because there is one big problem. So there are lots of systems now which have shown, this sort of quantum relaxation and so forth that is necessary to get a quantum computer running. Here are 2 examples which I won't go into. But the big problem that everybody's been talking about is the elephant in the room as far as quantum spin networks are concerned, and that's what's called decoherence. The problem is that our quantum spin network can entangle itself with the environment, and if it does that, we get what's called decoherence. The entanglement means that we can no longer track the degrees of freedom of this spin network or quantum computer. Now, the thing is, Parisi and company, when they were analyzing their classical models, they ignored this. And this was, of course, the big problem that the experimentalists had with them. They said, we don't care about phonons or all of this other junk, which is actually going to completely change the behavior. In some ways, they were very justified in the same way that, people who tried to understand chaos very early on tried to do it, first of all, with simple analytically tractable models. But you see, quantum computers are real things, and if we want to make them, we have to deal with them. And so it's actually, been touch and go for the last 20 years on whether or not one can deal with decoherence, but methods have been found so that people are a lot more optimistic now about the future of quantum spin networks than they were. The extraordinary coincidence is that although I'm working in quantum gravity, we just had a paper accepted for the letter today, which is precisely about getting rid of decoherence in the classic spin glass system. This is the so-called lithium, holmium, yttrium tetrafluoride system, which was the one for which the quantum annealing was first seen, and which has been analyzed more than any other spin glass system there is, both for the classical spin glasses by the people like Parisi, and for the quantum spin glasses. And so the fact that one can actually see coherent propagation, coherent modes in this system is actually a big deal. So you can see that this story has been going on for a long time. We'll probably, probably the community will date it from 1958, from Anderson's first paper. But it's certainly not finished because we're only really starting to explore the quantum version of the work for which Parisi was given the Nobel Prize. And people who live in Vancouver are quite fortunate because there are various companies now which are doing this. There's D-Wave, 1QBit, and so forth. And I believe that IBM is now moving a large lab to Vancouver to work on this. So some of you may get jobs with them. So that's all I wanted to say.